Thank you. Thank you, Giovanni, for this nice introduction, and also for inviting me to this nice seminar and for the opportunity to present the results. And hi, everyone. My name is Avci, and I will talk about chiral coupling between magnetic layers with orthogonal magnetization. This presentation includes results from my postdoc time at ETH Zurich, and all the results are unpublished, so it's still to be submitted. Yeah, then of course with the participation of my colleagues, Charles, Giacomo, and my previous advisor Pietro Gambardella. And I recently started to work in Barcelona at ICMAP, and with funding from an ERC starting grant. All right, chiral DMI has attracted an enormous attention lately. So the interfacial DMI, so in this kind of structures, forces the neighboring spins to an orthogonal orientation. And that has consequences on the domain wall. For example, domain walls, you can create nail-type domain walls in these structures or skyrmions. And the interfacial DMI and these non-uniform magnetic textures have been extensively studied during the past decade, leading to groundbreaking discoveries and innovative device concepts. Very recently, a theoretical prediction made by Vedmedenko and colleagues have shown that two magnetic layers separated by a non-magnetic material can also have chiral coupling. And this gives rise to a preferential direction of these two layers with respect to each other, and also some chiral spin textures on each layers. Soon after, there was also experimental verification of this prediction that these two there are two ferromagnetic layers separated by a spacer. In this case, it was a platinum ruthenium platinum trilayer, which is a non-magnetic spacer. And in these two papers, they have observed that the magnetization reversal behavior depends highly on the relative orientation of these two layers. But most of the experiments were performed on perpendicularly magnetized materials, so both layers were perpendicular. And the effective coupling fields were found to be relatively small, like on the order of a few millitesla. And they required kind of careful measurements to kind of resolve this kind of small changes in the magnetic reversal, magnetization reversal. But we know that in order to maximize the coupling, an orthogonal magnetic alignment would be indeed necessary. Such as like in the interfacial DMI, you have this domain wall, but in the interlayer DMI, it would be much more preferential if you can couple and orthogonally aligned magnetic layers. Indeed, similar, yeah, I mean, recently, so these are orthogonally, like coupling between orthogonal layers have been demonstrated in lateral structures. So you have here an in-plane cobalt and out-of-plane cobalt. It was kind of shown that they couple to each other through DMI, and switching one of them would lead to switching of the other one. So motivated by this, we have actually designed a system that could lead to a large DMI. And today I'm going to show that we can actually measure these layers and show that there's a strong DMI coupling in between these kind of structures. So we have here a cobalt that is in-plane magnetized, and terbium iron, which is perpendicularly magnetized, separated by a platinum spacer, the thickness was kind of varied between 1 and 3 nanometers. And we fabricated these kind of devices to measure Hall effect as well as longitudinal resistance. And to confirm actually that these layers are indeed orthogonal to each other, we performed a Hall effect measurement with an out-of-plane field sweep, which is basically the signal is proportional to the out-of-plane magnetization. This is a raw data taken from this kind of devices with 1.2 nanometer of platinum thickness, platinum spacer. And we can decompose this into a perpendicular contribution coming from terbium iron and an in-plane contribution coming from cobalt. So as you see, that cobalt has a typical in-plane behavior, which whose magnetization rotates out of plane with an applied field, and we have the coercivity here for the terbium iron. And now that we know that they are like basically perpendicular to each other, we can check whether there's an interlayer DMI in this structure. So we tested this kind of, so we came up with this kind of measurements. So you have here a magnetic field that is swept at an oblique angle, like slightly away from the out of plane direction, such that for a positive applied field, for example, in this case, in sweep 1, positive applied field, you would expect the cobalt like top layer to be right magnetized and the bottom layer to be up magnetized. So this for positive field you have right up magnetization, and for the negative applied field you have left down magnetization. And in the second sweep, in the second measurement, we do the same kind of sweep, but like now we change the angle to the opposite oblique angle. And then we expect that for a positive field, we have left up magnetization, and negative field, we have right down magnetization. And as you can imagine, if we are actually, if we are sweeping the field on the plane perpendicular to the D vector, the Dzyaloshinskii-Moria vector, then we expect that these two sweeps should give rise to a different coercivity, because you have an effective DMI field acting on the perpendicular layer that changes sign in these two configurations. So this is what I'm showing you here. So for this structure, we see here that there's a strong dependence on the magnetization direction, and we confirm that by doing these measurements as a function of an in-plane field, so in-plane angle. So in-plane angle meaning that the in-plane component of the field changes in the XY plane. And as expected from the DMI, we see that there's a sinusoidal behavior where we hit the maxima here when the applied field is perpendicular to the D vector, and we hit 0 when the applied field is parallel to the D vector here. So far, so good. So this is how we can measure the DMI effective field on the out-of-plane magnetization. Now I will explain you how we can actually measure it on the in-plane magnetization. So it's the same story. So we have an effective DMI field acting on the magnetization, and if you do the sweep for a fixed out-of-plane terbium iron magnetization, in this case, for example, for an up magnetization, and in this case for a down magnetization, and we sweep the field in plane, then we observe this kind of measurements. In principle, if there was no coupling, we would expect this V-shaped magnetoresistance curves that is centered around 0. However, due to this DMI effective field, that curve shifts towards one side or the other, depending on the terbium iron magnetization orientation. And we can, now that we have a way to quantify the DMI, like the shift due to the DMI, we can actually measure it on a series of like different samples. So as a function of platinum spacer. And as you see here that depending on the platinum spacer, the effect is, well, for the thinner samples, we have strong effect, and that decreases, well, the effect decreases and vanishes at about 3 nanometers of platinum. And we can actually quantify the DMI effective field by taking into account the geometrical factor coming from the field, well, the relative orientation of the effective field and the applied field. And surprisingly, we got more or less the same amplitude for these two effects. But it turns out that if you calculate actually this, well, if you convert the DMI effective field into a DMI interfacial DMI energy, and if you take into account the saturation magnetization and the thickness of each layer here, we found out that the DMI energy on both layers are approximately, well, are almost the same, and it's on the order of a few, like about slightly more than 40 microjoule per meter square. That is smaller than what you get in the interfacial DMI in, for instance, in the platinum cobalt, but still considerable, well, still large for this kind of measurements. And it's indeed comparable to other materials such as like tantalum or tungsten, like if you would kind of compare with the interfacial DMI. So next we did also a dependence on the spacer layer. So and this is the typical observation on the platinum. But then if you kind of, if you keep all other layers the same, and if you replace platinum by titanium, we see that the effect vanishes, well, within the noise. And we also checked other spacer layers, for instance, ruthenium, which was used in the original papers. And we saw that the effect is actually quite small with respect to platinum, still measurable, but quite small. And ruthenium is a material that gives rise to RKKY coupling, but it seems like it is well, the DMI mediated through ruthenium is not as effective as the RKKY. And we also checked another heavy metal, tantalum, and we also observed that the effect is actually pretty small. All right, and in conclusion, we designed a system and we measured the interlayer DMI. And we found that the exchange coupling, so the DMI exchange coupling actually can be quite strong. And it's, in our case, it reached 13 millitesla, but with more engineering, it could be even more like larger, because it depends on the ferromagnetic layer thickness and the spacer layer thickness. And we also showed that we can measure the DMI coupling on each layer independently. And then we also showed that, as expected, the DMI coupling kind of reduce, like gets smaller when the platinum is getting thicker. And we also showed that the coupling is stronger in the case of platinum, but much weaker in the case of titanium, ruthenium, or tantalum spacer. So with that, I would like to thank my colleagues at ETH, Giacomo and Charles, and Professor Gambardella for this project, and my current funding agency, ERC. And thank you for your attention.